Hello again. So now what we would like to do in this lecture is we would like to demonstrate onto an FPGA device how a simple circuit will work. The example we are taking is a counter which would be displayed onto a FPGA board. So the FPGA board we are taking is a basis board. So you can see here in the basis board there are switches here and there are some LEDs, and you can see there are 7-segment displays, there are some buttons here, and this is the FPGA chip. So to to see it onto the this is the reference manual of the basis 3 board. So it comes from Digilent, and it's a good FPGA board for practicing basic design for teaching purpose. So this is the block diagram here. So what you will see multiple things. So these are the switches which I have shown you, and these are the LEDs, and you see these are the 7-segment displays which can be used, and the input can be either taken using these switches or using these buttons. Now you also see there are several inputs, like we have USB input here, there is a Ethernet port here, and this is a VGA port. So because of this VGA port and Ethernet port and USB connections, because of this it can effectively work like a computer also. So the output can be displayed onto a monitor, and the keyboard input or a mouse input can be taken using this USB connection. And these are the general input output connections which can be connected to any of the sensors or actuators, etc. Okay, so this particular part help us to program whether it is programmed using I'll give a more. So here this particular plug, it helps us to give whether the power is using external or using USB, and similarly the connections whether so there are 3 ways to program this board, whether QSPI, JTAG or USB. So currently it is we have put a connection so that it can be programmed using USB. So in our board we have made this connection using USB, so that we can program using the USB. So this is the USB cable which can help us in connecting. The other thing which I would like to point out here is the numbers which are written here. So for example, this is the LED 0, and here E19 is written, and for LED 0 U16. So this is the U16 number is written. LED 1 U19 is written. So what is this U19, U16, etc.? So this is our FPGA chip. On the FPGA chip there would be various pins. These pins numbers are written here. That means there would be several general purpose pins. So the pins of FPGAs are connected to let's say E19. E19 is a pin number onto this Artrix FPGA chip, and that E19 pin is connected to this LED. So after looking at this this board schematic, now let's go back into design and see how the design process will work. So we will use because this board is coming from Xilinx, so we have to use Xilinx software which is called Xilinx Vivado. So this Xilinx Vivado is actually a free software which can be used. So here we are creating a new project, and when we create a new project, so let's say because we would like to design a counter, so let's say we want to design a counter. So this is actually 15 modulo 32 counter. So let's design a modulo 32 counter, and then it will ask us that whether it's a RTL project, post synthesis, IO planning, imported project, or example project. So I'll quickly tell you the difference. So RTL project is, now since we are designing our own project, and this will come under RTL project category. In post synthesis, that means we have already done design synthesis, then after synthesis we can use that synthesis and we can directly start from there. Imported project means that you have done project using some other software like Simplify, XST, or ISC, and then we want to do this. Example projects are there certain templates which has been predefined in this software. So if we would like to start with the example project, then we can start. So this one is a RTL project. So in the RTL project, now we have to specify what is the sources. So the sources I have already created into Verilog. So there is a counter here. I have to so there I have already created this count.v. So that we will import, and then we'll go to the next step. Yes, so in the next step we have to add constraint file. So what is this constraint file? We'll come to this in a little while. So this constraint file will tell that which input output is connected to which particular pin of the FPGA. So I have already created this constraint file. Let's add this also into the design, and then the next step. The next step is finding which particular part or which particular FPGA board. So now how do we find out that? So if we see this FPGA board, here it is written that which particular is the part number. It says Xilinx RTX 7 and XC7A35T. So this part number we will choose, and how to choose this part number. So first thing, we know that it's an RTX part, so we say the family is RTX 7, and then we further select the package. So if we see from the specification, the package is 236 CPG 236. So that give us the limited options. So from the limited option, the one which is ours one is XC7A35Ti CPG. So we selected this part, and now we can finish creating this project. Now we need to add our test bench also. So let's add one more source which is called simulation sources. So in the simulation sources, we have added another file which is testbench.v. Okay, so this is we have done. Now let's also see what is this Verilog file, so that we can the module name is called Blink, and it has three inputs: clock, reset, and count. The input is clock and reset, output is 5-bit count, so that's a 32-bit counter. So 32 modulo 32 counter. And now we see the count. We have created two more registers, count reg as well as a 32-bit counter. Now you see this design here. We are saying at every edge of the clock and reset, we are making counter equal to 0, and counter is being incremented at every clock cycle. Okay, so if reset is not there, which won't be there, so if reset is not there, counter is incremented every clock cycle. So now because our clock is going to be very fast, so typical value of the clock is 100 megahertz. So 100 megahertz is very fast, so if that will run, we'll not be able to see what is happening, so we have to slow down that. So if counter value increases beyond certain limit, then we are saying the counter has to become 0, and the final count reg, which we would like to give as output, would be incremented by 1. So this incremented by 1 would happen only when the counter is more than this large value. Now then we are assigning count, which is our output, to counter. So counter is assigned to count. So this is a very simple design, certainly at RTA level. And now let's also look at the constraint file. So in the constraint file, if we see, the constraint file is specifying that my clock has to be connected to W5 pin of the package. And here we are saying that the clock is actually having a period of 10 nanoseconds, so that means 100 megahertz clock. And we are saying count 0 pin is to be connected with U16, and count 1 pin is to be connected with E19. So so on and so forth. So basically this is LED 0, LED 1, LED 2, LED 3. Reset is connected to central button. So this so that whenever we would like to reset, we can press the central button. Okay, so this is how we are binding our input and output to the input output which are specified on the FPGA board. Okay, in the test bench, the test bench has in the test bench we are simply giving the initial, initially we are saying reset equal to 0, then clock equal to 0, and then forever basically we are saying clock equal to not clock. Okay, so this clock equal to not clock would keep on happening, but a reset would happen only in the initial stage, and after that reset will remain 0. So once it is done, we have to first we have to run the simulation to see whether things are correct or not. So the whole process is in the same fashion. So basically first is the designing of the in the left pane. We can see initially we have to create the project, and after that we have to, the second step is simulation. So let's do the simulation part, and we can do only behavior simulation, that means functional simulation. So this functional simulation would help us to check whether our circuit is correct or not. So during the simulation process, you can also see that it is doing execution, it is doing elaboration, and so after doing elaboration step, then it will start the simulation phase. Okay, so now you see this panel automatically coming which is saying test, and then this is the B block. In the B block we have a counter array. So this is our test block B, and there is a counter. So let's also add this to our you remember there are two things. One is count, which is a 5-bit counter. The another is a 32-bit counter. So we add this also to a wave window. Okay, so if we try to run now, we have to run it for a while, then only we can see something which is happening. So during this using minus or plus, we can see that how values are being changed. So this clock is changing every time, and similarly this value of count is also being updated every time. So now I am running it for 10 seconds because the value of count will increase at every clock period. But the value of count, which is a 5-bit count, can only change after that the counter value is large enough that it can change the value of count. So we'll not run the complete simulation, but at least we'll reach to certain stage so that we can see whether our count is increasing or not. So here you see that every clock my counter is increasing, so it's changing. We can, if we zoom onto this window, then we can clearly see whether it's increasing by 1 or not. but after some time you will see that this 0 0 will become 0 1. That means my count is increasing, and that also signifies that my functional simulation is correct. So let's wait for a while. You see, after 1 million nanoseconds, this has changed from 0 to 1. So we can pause it for now, and if you want to see in detail, then we can see. By clicking on this pause button, the simulation would be paused after yes. So there you can see the simulation, and now if we try to do a zoom out, then we can see that it changed exactly at 1 million nanoseconds. So 1 million nanosecond it changed from 0 0 to 0 1. So similarly, after every 1 billion nanoseconds, it will keep on changing. So the idea here is that at every 1 second it would change to a new value. Now after our simulation is correct, then the next step is we have to go through the synthesis process. So we click on the run synthesis step, and then we will see that how synthesis will go on. After synthesis is completed, we see this window that now it is suggesting that either we would like to run implementation, open synthesized design, or view reports. So let's go ahead and look at the reports. So we can see from there that what has been done after the synthesis. So this is the synthesis report. So if we see, there are two reports here. One is synthesis report, another is report of utilization. So the synthesis report tell us various information. It says that how much time it took, and it also tell us various kind of analysis, like how many it says that in the RTL component there were adder of 5-bit, and there are register which is also 5-bit registers. Total number of DSPs and BRAMs are the total number of BRAMs and DSP which were there, but looks like nothing was utilized. But this report will tell us that how much is the potential utilization factors. Okay, in the end it also tell us about the what would be the potential or estimated resource utilization. Buffer is 1, carry units 4 is 7. So there are 7 carry 4 units are used. This carry 4 are you remember that we have in each slice there are 4-bit carry which can be utilized. So this is the cell which has automatically inferred by the synthesis tool, and it has used 7 of them. LUT with single input is used once, LUT with 2 inputs, LUT with 3 inputs, 4 inputs, and 5 inputs. So basically, although there were only 5 input LUTs, but they have been we can utilize into different formats. So that's why different so that our utilization could be complete. So you see the 6 input LUTs are also 29 which has been used. These are the flip-flops which are also 34 in number, and input buffer, so there are 2 inputs and 5 outputs, so that's why iBuff and OBuff is used. So this give us the overall estimate how much time, what is the timing analysis, and also the resource utilization. So after looking at these reports, then we can run the implementation. This is the second part. So as I suggested earlier in the earlier part of this lecture, we can also go for post synthesis simulation, but let's skip that step for now and we go for a implementation part. So the second part is the implementation. When we run the implementation, then it is asking how many number of jobs. So this help us to do things in parallel. So we are trying to use 4 processors on the computer, and then we run it. Now the implementation process is complete. So after implementation process, we can go ahead and look at the reports. So if you see here, the type of reports we have generated is you can see in the left panel that there are reports for timing, reports of clock network, report of methodology, report of utilization. So and we can also look at the implemented design. So if we open the implemented design, then we can also look at some of the interesting aspects of the FPGA. So this is the overall layout of our FPGA, that it has the FPGA has been divided into 4 different physical parts, and then let's look at, we see that this is after placement and routing. So this is the after implementation. We can see there is some logic here, so we can zoom this part and then look at this area. So if we further zoom in, then we can see that this is clock region, and and so by browsing we can see that the multiple clock registers. So these clock registers are helping in their multiple clock registers, so that clock could be buffered. The major part of the design is onto this part. So if you see, let's look at even further. So we can further make a zoom in onto this part. So so you see, this is one CLB. We can further zoom it to see what is there inside. So internal structure is being shown here. Now it is showing that this is the counter reg. So the register which is a 32-bit counter, so that 32-bit counter is also being incremented every time. So that means it would require you can see there's this part of the slice. So this is one slice. In this one slice there are the 4 LUTs. So all the 6 input LUTs are used, and further this is the counter part. So basically the addition which is happening. So this is the carry chain. So you can see the carry chain which is going from here to here. So this carry forward chain module has been used, and 4 of the registers has been used. And similarly this is another part of the counter which is being used here. So you can see the utilization of the resources. Interconnect is not shown, but at least the physical placement is shown. And another thing to notice is that this is all the parts, all the basically all the logic is placed nearby, so that this would have minimum wire delay. And also the if we see the input and output, So these are the U19, V19, these are the pins where the pins are physically placed. So because pins are here, that is why all the logic has been placed on the nearest CLBs which were there near these pins. Okay, so this physical view or the physical implemented design can give us an idea that how which part of the FPGA has been used and which particular logic has been used. Okay, so if you would like to explore it further, you can install this Vivado software, and you need not to have FPGA board, but still you can explore how different units are there and where they are placed, and all that kind of analysis can be done. So the in detail we can see all other reports also, for example design rule check, noise, utilization, power. So here it clearly says that out of 20,000 LUTs, some 38 LUT has been used. Out of 41 registers, 32 registers has been used, and total number of 14 slices has been used, and LUT as a logic is 38. So sometime LUT also can be used as a memory. So all of those things will come in the utilization report. Okay, so this is how we can look at different reports and analyze how the circuit has been implemented onto the FPGA. The last step of the process is to generate the bit stream. Now we will generate the bit stream. So now the implemented design clearly say that which particular CLB, which particular slice, and how they are configured, which logic has been configured. So all those things, all this information is there. Now given the which particular device is there, so based on that the bit stream is generated. So let's wait for some time till our bit stream is generated. Now bit stream has been generated. So after bit stream has been generated, the next step is we have to download the bit stream onto the hardware using the hardware manager. So we have to, now we can open the hardware manager so that we can see where we can install that bit stream onto this. So hardware manager can also be opened here. So now this is the hardware manager which is here. Now we see here there is a auto connect. So basically if there is a FPGA unit which has been plugged in, it will try to identify whether there has been any FPGA which is connected, so it would be able to explore and see which particular FPGA is there. After this exploration, you see that XC7A35, this particular we can see our basis board which is present here. Now if we right click onto this, and then we can say program device. So using the program device, we have to now first of all tell where is the bit stream. So the bit stream path need to be given. The path would be there in the project directory. In the project directory, we have to see in the project.hardware, and then there is a hardware.1, and then we can see sorry, it's not there. It would be there in .runs, and here it's a implementation. In the implementation, we can see a bit file. So this bit file we can use, say OK, and we can say program. So during the program phase, it would be downloaded onto the hardware, and I am putting this in front of you so you can see that these are blinking in a fashion. So if I press this button, then it will again reset and it will start from the 0 1 2 3 4. So again, if I press a reset button, it will again start from the 0. So this way we see that although our module is sitting on the FPGA, but it is connected to these LEDs and also the central pin, which can help us to reset. So this is how the whole process will work, and this demonstration can be helpful to design or to see that we can explore more. So you can you would have a question that if I don't have a FPGA hardware, how can I do experiments? So that question is correct. So FPGA hardware is also a bit costly, but this software which is coming from a vendor like Xilinx or Altera, so those software are usually free, and we can at least go to the stage where post layout, or basically after placement and routing, that kind of analysis can be done, and but actual testing can be done only on the board. That will always remain the fact. So if you get access to these boards, then that is wonderful, but there would be some schemes, or there would be we hope that sometime there would be we would be able to access some of the FPGAs on cloud, and then we would be able to remotely access them. So that could also become one of the possibility to do experiment on FPGAs. So with this I would like to close, and I would like to I would expect that you would also do at least some experiments, so that you can go through this whole process and can explore that how much is the resource utilization, how much is how you can do static timing analysis, etc. Okay, with this yeah, thank you very much.